Hello viewers, welcome to Codifos. In this video we are going to discuss about the last year CSIR net question paper part C, first question, which is given in the Indian the CSIR net is conducted by the National Testing Academy of India, which is affiliated to Government of India. In this examination there is a ton of disciplines. We have to write examinations which is meant for researchers, professors and etc. Most of the people write these kind of examinations to get more onto research. While preparing for this examination, I got an idea to share my study notes with others too, so they can easily understand how the question pattern would be there and how to solve the equations. For now, as of now, I just having the last year 2025 December UGC net CSIR net question paper right in my hand. You can see on the screen question number 46 from part C. This is the first question in part C. Consider an emission line of wavelength 550 nanometer, lambda is equal to 550 nanometer of argon gas, which is at atomic number is A is equal to 40 and which is Z is equal to 18 at a temperature of 400 Kelvin. The full Doppler width of the emission line will be closest to. In this we are going to find out the Doppler width of emission. Before on that hand, we should know what is the this subject is meant to be. First of all, atoms or molecules, when they are stationary, let us consider this is a molecule or an atom. When they are stationary, they would emit a wavelength. Let me call it as a wavelength lambda. This is a wave. This is a particle which is emitting wave. That would be lambda naught or lambda 0. This is a standard wavelength. But in practicality, atoms would be travel like here, there and there. We know atoms are distributed everywhere, they can travel anywhere, and this kind of motion is called thermal motion, which is called as thermal motion of an atom, which is called as thermal motion of an atom. Okay, let me rub down this all here. 1 minute. Let me rub this down, maybe like this. Using this we can rub this both. Okay. Okay, we are clear now. This is like there is two conditions over here. Like if the atom emitted from a particle, or if an atom or a particle emitting a wave which comes around a lower frequency, like the wave comes in a lower wavelength, the wavelength is small. Let us consider this is small wavelength. This is coming in a small wavelength. This is called blue shift. Here we are calling this as blue shift. Or if the wave is coming at a higher frequency, higher wavelength, this is called as red shift, which is the main agent of the Doppler waves. And in a gas sample, there may be millions of atoms are roaming here, there and there. They are roaming here and there and there. with the help of Maxwell-Boltzmann distribution, we come at a particular spectral line which is called as Doppler broadening. Like, we can't find each and every wavelength of each and every atom. We have to quantize it. So we are using a spectral line called which is called as Doppler broadening. This is the main concept here, Doppler broadening. Okay, let me wipe down all of this. 1 second. For this, we have a mathematical formula, full wavelength at half maximum, which is known as, for our particular problem here, we have a particular formula called Gaussian, which has a form of Gaussian distribution. Let me come to our problem. We have an emission wavelength of 550 nanometer, argon gas, temperature at 400 Kelvin, and we have to find the full Doppler width of the emission line. We have to, like the Doppler broadening, we have to find the full Doppler width. For that, we are having delta lambda d, which is equal to 2 lambda naught, which is, we already discussed that this is the standard wavelength when the particle is at rest, and we have a square root of 2 kb. I will share the formula in the description also, so you can easily understand it. T is the temperature, kb is the Boltzmann constant, natural logarithm ln of 2, and whole divided by m, the mass of the atom, c square, mc square. This is the formula itself for the thing. Let me came here, let we are opening another tab here, and here also we are going to, 1 second. Let me zoom it in, zoom in. Next time I will sort out this kind of issues before starting the classroom. Okay, and for that we should have to calculate. First of all, we have the values here. For argon, A is equal to 40, which is given in the formula itself. Z is equal to 80, which is also given in the formula. Lambda is equal to 550 nanometers, I think so, which is tends to 5500 Armstrongs, I think. If I correct, that is value 5500 Armstrong, which is comes under the visible range, and T is equal to 400 Kelvin. Once again, 400 Kelvin. Okay, and we already know that kb, or one of the most famous formulas, the Boltzmann constant, which is 1.38 into 10 to the power of minus 23 joule per Kelvin. The unit is way too important, and here comes our superstar, 3 into 10 to the power of 8 meter per second. We already know that the speed of light here. And for this mass, where we can find the mass, once again, the mass is 40, A is 40, so the mass of the atom is 40 into 1.66 into 10 to the power of minus 27 kilograms, which is the atomic unit. So the mass would come around roughly 6.64 into 10 to the power of minus 26 kilograms, which is already pre-calculated values I have calculated. There may be some issues, but kindly follow the process, and if you found any mistakes on this calculation, you can surely mention them on the comment box also. I will sort it out. Once again, we will open a next window here. I think okay, that is visible. Here we have a condition. The order of the magnitude which we have to find out, there is a shortcut formula is called lambda d divided by lambda. The change in the Doppler wavelength divided by the wavelength is approximately equal to the thermal velocity, the ratio between the thermal velocity and the speed of light. Here we are finding out that order of magnitude, the wavelength of the Doppler frequency, also the wavelength is approximately equal to the thermal velocity divided by c. This is a condition we have to study about it. If you have any doubts or further on this topic, I will give a detailed lecture on the next video. If you have any doubts, you can ask in the comment box. This thermal velocity have a value which is Boltzmann constant in the temperature divided by mass in a square in a root, and we are going to calculate this kpt. We are going to first calculate this kbd. I have already pre-calculated this value, which is around, this is, you already know that this is around 1.38. This comes around 400, so we get around 5.52 into 10 to the power of minus 21 joule. Here you can find there is minus 21 joule. Okay. Also we are going to find out the mc square value, which is also a pre-calculated value. Here I will paste it, which comes around 5.976 into 10 to the power of minus 9 joule. Okay. These all are the pre-calculated values. After that, we are also going to calculate another value. Let me wait once again. I am spending quite a lot of time for a single sum, but you cannot spend this much of time for a single calculation, because in the net or gate examinations, time is the major key for your success. So which is approximately equal to the kbt and the mc square, which is approximately the ratio between two are approximately equal to 10 to the power of minus 13. Okay, and when we take square root of it, we already know that approximately it comes around 9.6 into 10 to the power of 7, which comes around 9.6 into 10 to the power of 7, which is the value we are getting right now. For Doppler, the change in Doppler value, lambda d, delta of lambda d, which is equal to 550 nanometers into this value. Scale came here, and we get around 5.28 into 10 to the power of minus 4 nanometers. Okay, which is the value we are getting here. And here we have to add the natural logarithm to this value. We didn't add the natural logarithm earlier. We find out here there is a 2 into ln of 2. We didn't add the value. When we introduce the value here, we will get a final value. I will write here final lambda d. I am writing this in main area. I will change the color also. The final value we get around, that natural logarithm value comes around 2.35 into this 5.28 stuff, we get 1.24 into 10 to the power of minus 3 nanometer, which is 1.24 nanometer. Let me dive into our question paper. We get the value of around 10 to the power of minus 3, which is the correct value. 10 to the power of minus 3 range. We are getting the value in that 10 to the power of minus 3 range here. 10 to the power of minus 3 nanometer, which is the answer. This sounds like a pretty interesting question. Let me revise once again. This is the formula here for the Doppler density, which is called as Doppler density, which is the formula here. This is the standardized value here, 2 into 2 lambda 0. This is the formula. Afterwards, we are going to change we are writing the given values here, the atomic number, given nanometers, temperature, etc. All the values we are writing here. We have find value of m here, and here we are using a condition called the ratio between the Doppler density and the wavelength, which is approximately equal to the thermal velocity divided by c. So our calculation would become some amount of easier stuff. So we are applying this formula here. We are computing all the values, necessary values here, and after computing all the necessary values, we are pasted down all the values here, and we finally found out the result. This is the detailed calculation of the first question, which is consider an emission of wavelength lambda is equal to 550 nanometer of argon gas at temperature 400 Kelvin. The full Doppler without the emission line will be closest to 10 to the power of minus 3 nanometer. I hope you got a better idea on this video. If you have any doubts, you can directly comment. Also subscribe to the YouTube channel, and if you have any doubts, you can directly ask me in the comment section. Also, I will provide a Discord link especially for this. So in that place, we will have discussions about the net examination. We will open a Discord page, and I am Sri Kalishwarar, an MSc pursuing student from Tamil Nadu. I am also trying to crack the net examinations. We will study together and we will learn together. See you in another video. Thank you guys.